Let's take a look at electric current and Ohm's law. Let's start off with current. Current is defined as the amount of charge that flows past a cross-section of wire in a given amount of times. Current, we're going to use the symbol I, and of course we already have a symbol for charge and for time. So this is the definition of current. Current has a unit known as the ampere, which we abbreviate with a big A. So using this formula is pretty simple. It's got three variables in it. Let's do an example real quick. A steady current of 2.5 amps exists in a wire for 4 minutes. How much total charge passed by a given point in this time, and how many electrons would this be? So if you look at our relationship up here, that current is charge per time, we want to know the amount of charge. So we'll just multiply both sides by T, and we'll get that the amount of charge equals the current times the time. And then we can put the numbers in. That was 2.5 amperes, and the time was 4 minutes. Now, 4 minutes, if you multiply that by 60 seconds per minute, is 240 seconds. We need to have our times in seconds. So that's 240 seconds. And if you plug that in the calculator, you get 600 coulombs of charge. Okay, that's part A. Now part B, how many electrons? Now here we can go to our definition of the amount of charge in an electron. So if I have 600 coulombs of charge, in a way this is like a conversion, and 1.6 times 10 to the negative 19 coulombs per electron, so to speak, will give us a total number of 3.8 times 10 to the 21 electrons. And that's your definition of current. Ohm's law lets us understand how current is created. In a way, I think of it as the Newton's second law of electric current. So current has a cause. The cause is a voltage difference from one point to another point inside a conductor will cause charge to flow. Now, how much charge flows is directly proportional to that voltage, but it's also inversely proportional to what is known as the electrical resistance of that wire or circuit. Okay, this could be an entire circuit. Voltage is what causes the current to flow. Resistance is what resists it. Why this reminds me of Newton's second law is because when we said that acceleration was caused by a net force and resisted by mass. So it really does have a similar parallel. The cause is on top, and in a sense, resistance is like electrical friction, whereas this is inertia. Ohm's law is insanely useful. You can use it for entire circuits. You can use it for individual components in a circuit. The first thing we need to do is look at this thing that's new to us, which is resistance. Resistance, again, the electrical resistance in a circuit is measured in the units of ohms. What a shock. It's named after the guy whose the law is named after. And the symbol for this is a Greek omega, the kind of horseshoe looking one. Let's do an example, and then you can practice on your own. A small flashlight bulb draws 300 milliamps from its 1.5 volt battery. A, what is the resistance of the bulb? And B, if the battery becomes weak and the voltage drops to 1.2 volts, how would the current change? Alright, let's start off with A. We have that the current is 300 milliamps, which is 300 times 10 to the negative 3 amps. And that the voltage is 1.5 volts. And we need to know the resistance. If you solve Ohm's law for resistance, you're going to wind up with the voltage over the current. And we have 1.5 volts over a current of, if you do the conversion, you get 0.300 amperes. Plugging it in the calculator will get you 5 ohms. Alright, so now we know the resistance of the light bulb. That's a physical property of the light bulb. That's not going to change when the voltage changes. But what will change is the current. So the voltage is now dropped to 1.2 volts, and the resistance is still 5.0 ohms. Solving for, we don't have to solve anything. Ohm's law is already in terms of current, and that's voltage over resistance. So now we have 1.2 volts over 5 ohms, and we get 0.24 amperes, which is 240 milliamps. So what you can see is if the voltage drops, so does the current. That makes sense. Current is directly proportional to voltage.